Hi everybody. In this video, I am going to discuss about Schrodinger's time-independent wave equation. We know that Schrodinger's time-independent wave equation is one of the fundamental equations in quantum mechanics. In fact, Schrodinger's time-independent wave equation represents the quantum object that is represented by a wave function, complex wave function psi. Now the psi is generally a function of the space coordinates x, y and z in 3 dimensions and the time coordinate t. For the time independent derivation, we have to ignore the time dependence of the wave function psi. Now this wave equation of Schrodinger is similar to the Newton's equation of motion for a classical object. So this equation signifies the behavior of the quantum object. Therefore this is nothing but an equation of motion in quantum mechanics. So Schrodinger's equation is nothing but an equation of motion of a quantum object represented by a wave function psi, which is a function of spatial coordinates x, y and z and the time coordinate t. Since first to begin with we are going to deal with the time independent wave equation, we can very well ignore the time dependence of this equation and we'll first stick to only the spatial dependence of the wave function. Therefore, at a later stage in another video, I'll also post the entire derivation and discussion on Schrodinger's time-dependent wave equation. Right. Some basics have to be first clearly understood before we proceed to derive the wave equation. What are those important points that we should remember? First, the wave function psi of x, let us say, if there is only the one-dimensional equation that we want to consider, then the wave function is only a function of one spatial coordinate x, psi of x, and for the time-independent wave equation, though the wave function as such is a complex function, having both real and imaginary parts, we can for the time being ignore the imaginary part and assume that the function is only a real function. Though in reality, a complex function has both real and imaginary parts. So in the entire derivation, we will start assuming that the wave function is going to be only a function of one spatial coordinate x, and then we will generalize that to three spatial coordinates x, y and z. And not only that, the complex wave function has only the real part and the imaginary part is assumed to be equal to 0. This is how we'll do some assumptions in the beginning and start deriving the equation, and once we've derived it in very few steps, we'll be able to kind of generalize it at a later stage for more realistic cases. Right. Now wave function has very interesting properties. For example, if you want to consider the physical significance of wave function, it has to follow, though it is just a mathematical function, it kind of represents some level, at some level, some physical reality as well. So this mathematical function, which is a complex function, has to obey certain very important things. So in another video, to which I will provide the link in the present video, I'll discuss the entire significance of the wave function. So please do look out for a video on significance of the wave function in quantum mechanics. Right. Now let us proceed to derive the Schrodinger's time-independent wave equation in few simple steps. Right. Let us assume that the wave function psi of x has the form a sine k of x. I already mentioned that we are considering only one spatial coordinate x to begin with. Then we'll extend it to 3 spatial coordinates, that is to 3 dimensions. When we do for one spatial coordinate, this is obvious that we are first trying to derive Schrodinger's time-independent wave equation in 1 dimension. So we are assuming that this is a trigonometric function, the wave function. Particularly here it is a sinusoidal function, and the argument for the sine function is k into x, where x is the variable parameter, and as the x varies, the wave function psi varies. Now what is this k? K is called the wave number, and numerically this k is equal to 2 pi over lambda, the wavelength of the wave. This wave is obviously nothing but the de Broglie wave in quantum mechanics, because according to de Broglie's hypothesis, every quantum object having a mass and which is moving with a velocity will have a momentum, let us say p. Then the de Broglie wavelength for such a particle is given by lambda, which will be equal to Planck constant h over the momentum of that object. This is the de Broglie's hypothesis in quantum mechanics. Right. It's very important to remember some of these fundamental ideas in quantum mechanics to derive the Schrodinger's time-independent wave equation. Right. Suppose if the total energy of such a particle is E and the potential energy is V, then the kinetic energy of the object when it is moving is the difference between the total energy and the potential energy. That is the kinetic energy of this object. Therefore, the total energy E is given by, in the absence of a potential energy, just E is equal to P square by 2m. If there is a potential energy involvement, then obviously this is going to be E minus V is equal to P square by 2m, and therefore this momentum P can be expressed in terms of the kinetic energy as 2 times the mass of the particle multiplied by the difference in total energy and potential energy, that is the kinetic energy. So the momentum of this particle can be expressed as P is equal to 2m multiplied by E minus V. Now these are some of the equations that we'll be using while we derive the Schrodinger's time-independent wave equation. Right, now let us proceed to derive the equation. First, we know that we have assumed that this is psi of x is equal to a sine kx. Now, any wave equation in reality is, if suppose the wave function is f of x, then the wave equation will be having second derivative in both space and time. That is the general form of any wave equation, for example, representing waves in the ocean. Therefore, under such circumstances, one can write a general wave function as 1 by v squared. V is the velocity of the wave. Dou square f by dou t square is equal to dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square. You can see that this equation is a general wave equation. For a wave function f of x, which is the wave equation is having a second derivative both in temporal coordinate and 3 spatial coordinates. Of course, v is the velocity of this traveling wave. This is the equation of motion, or this is the equation for representing a wave in classical mechanics. Now, our de Broglie wave is somewhat similar to this, but the difference is the f of x that we just now discussed is a real function. It is not a complex function. But the wave that represents a quantum object happens to be a complex function. Right. Now we can proceed on to therefore take two derivatives of this complex wave function psi of x, and then we can arrive at the Schrodinger's wave equation. The first derivative, because it is, for the time being, it is a function, the psi of x is a function of one spatial coordinate. I am taking just the general derivative, so dou psi by dou dx, d psi by dx is equal to, a is a constant, it's still unknown constant, arbitrary constant of the equation, and sine kx is k cos kx. If we take the second derivative, d square psi by dx square, then a into k cos kx, derivation is minus k sine kx is the derivative of cos kx. Therefore, the second derivative of the wave function psi happens to be equal to minus k square a sine kx. Right. This is again nothing but the originally assumed wave function psi. So this can be expressed in terms of the original wave function. Therefore, the equation now happens to be d square psi by dx square is equal to minus k square psi. Right? Therefore, we can write d square psi by dx square plus k square psi is equal to 0. This is the first step in the derivation, and this is now a second order differential equation having this particular form. Now we have already defined what is this wave k parameter, which is nothing but wave number. So this is wave number. So we can substitute 2 pi over lambda in this position to again write this as d square psi by dx square plus squaring the whole thing becomes 4 pi square by lambda square psi is equal to 0. Now we know that de Broglie hypothesis tells us that this de Broglie wavelength lambda is nothing but h over p. Substituting that here, we can get d square psi by dx square plus 4 pi square by h square p squared psi is equal to 0. So this is nothing but d square psi by dx square plus 4 pi square p square divided by h square psi is equal to 0. Now I am going to use this portion of this board for continuation of the derivation. Right. Now, for convenience, we can use another common thing, that is, instead of 4 pi square by h square, we can use 1 by h cut square. Where h cut in quantum mechanics is nothing but h by 2 pi. So h cut square will be h square by 4 pi square. So 4 pi square over h square will be 1 by h cut square. So we can write this expression again as d square psi by dx square plus, from here, p square divided by h cut square psi is equal to 0. Now p square is 2m multiplied by, from here, E minus V. So if E is the total energy and V is the potential energy of the particle, then we can write, instead of p square here, d square psi by dx square plus 2m E minus V by h cut square psi, of course, is equal to 0. So this is the time independent Schrodinger's wave equation in one dimension, because we have considered only one spatial coordinate x. Now we can extend the same equation to 3 dimensions and write as d square psi by dx square plus d square psi by dy square plus d square psi by dz square, because now psi is a function of 3 spatial coordinates. What we have to use is partial derivative, so it should be actually dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 2m over h cut square multiplied by E minus V of psi is equal to 0. So this is the Schrodinger's time independent wave equation in 3 dimensions, 3-dimensional Schrodinger's time-independent wave equation, the most general form. Now, this can be mathematically written more elegantly by using the Laplacian operator. What is the Laplacian operator? Del square is equal to dou square by dou x square plus dou square by dou y square plus dou squared by dou z square. This is the mathematical operator named after French mathematician Laplace. So this operator is called Laplacian. Now using this operator, I am going to write this equation, that is Schrodinger's time-independent wave equation in 3 dimensions in a very elegant form on that side. Right. Therefore, we can write the same equation as del square psi plus 2m by h cut square e minus v of psi is equal to 0. So, this is the Schrodinger's time-independent equation in 3 dimensions, written in a very elegant form using the what is called Laplacian operator. Okay. So, this is our Schrodinger's time-independent wave equation. Now, suppose if the particle is a free particle, that is, no force is acting upon the particle, then the potential factor V is going to be 0. That is, the potential energy is 0. That means we can make this part 0 and write for a free particle a derived version of the Schrodinger's wave equation. So, for a free particle, V is equal to 0. Therefore, the Schrodinger's equation is del square psi plus 2m over h cut squared E psi is equal to 0, because now our V is 0. So, this is the Schrodinger's time-independent wave equation for a free particle. Right. Thus, we have derived the Schrodinger's time-independent wave equation using a few very simple approach, ending up at the Schrodinger's time-independent wave equation for a free particle. We started assuming the wave function to be a trigonometric function of sinusoidal form, because all waves can be represented as a combination of trigonometric functions, sines and cosines. So we started from there, and then we have taken 2 times derivative because we know that any wave equation is generally a second order differential equation. So we have taken 2 derivatives, first derivative and then second derivative. Then we have used the known ideas of wave number, expressions for wave number, as well as we have used expressions for de Broglie wavelength. Using all these expressions, we have been able to arrive at the Schrodinger's time-independent wave equation. Here in this process, we have also used what is called Laplacian operator to express the Schrodinger's wave equation in a more elegant, compact form. Then we have further been able to reduce the Schrodinger's time-independent wave equation for a free particle by assuming that potential is 0. If the particle is free, no force acts upon the particle, therefore the potential is 0, and hence the potential energy V is 0, and hence we have been able to finally arrive at this compact form of Schrodinger's time-independent wave equation. Please like the video if you have learned how to derive the Schrodinger's time-independent wave equation from this video. Also, please look out for the another video on Schrodinger's time-dependent wave equation. Thank you.